So that's what we're going to do now. So the last two classes are about the binomial distribution. Today, we turn to what's called the normal distribution. So this is actually probably one of the more ubiquitous distributions in just modern life. I've referred to this thing since probably the beginning, the very first day of class. In many ways, this distribution affects your life without you even knowing it. And that can happen in a whole slew of ways. If you're paying attention to the news now, you hear a lot about the pandemic, and you hear a lot about flattening curves and all this this talk. And one of the first steps to even understanding the actual math and science in these ideas of flattening curves and exponential models, blah, 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 the very foundation of understanding any of that would start with your understanding of what we're going to start today. So while everybody sort of thinks they're experts on this in real life, very few are. And we're not saying you're going to be an expert on it, but we're saying that if you ever hope to truly understand these quote unquote equations / models, this is the piece that is at the foundation of that, metaphorical building. Okay, so just a few background things that we need to sort of review from maybe your algebra class. So let's do that. Not scary algebra, although what we're going to write might seem very scary. So let's review a couple things that are likely to come in handy. For those of you playing along and trying to learn this. So given certain equations, this pen, the time to be alive. So if we have a certain relationship that is an equation, you guys are aware that we can visualize that relationship using a graph. You've done this probably since 7th or 8th grade, the very first time you encountered algebraic sort of equations, as it is, where you're relating two quantities. For example, you guys, one of the first things that you would study would be a linear equation. And what is a linear equation? It's something that looks like y equals mx plus b. And this thing, as you might recall, has this number m is called the slope. That tells us how steep the line is. This number b, whatever it is called the y-intercept. And if we wanted to graph one of these, we could, just to remind you. If I do my XY coordinate system, let's take a color. So let's take a specific example of one of these. You might have something like y equals, how about 1/3 x minus 2. So one way that you can interpret this sort of equation is that it crosses the x-axis at a certain point, it crosses the y-axis at a certain point. This guy crosses the y-axis at the point 0, -2. That's the y-intercept. And it crosses the x-axis at the point 6, 0. So this pink line is a sketch of this particular equation. And you could label these points. Clearly, I'm not drawing them to scale. That's okay. Not the end of the world, but this is -1 and then 3. 1, 2, and then 4, 5, and then you have 6. And it's not the scale, but put that to scale. So again, most of you know this. That's great, but that's not the point. We're not asking you to remember, be an expert at linear equations right now. The point I'm trying to make is that one of the first things you studied is if you had two quantities that are related, we'll call one x, we'll call the other y. And this relationship that I've written, y depends on whatever x is, and we can visualize it in that sense. And then you graduated to different types of equations. You guys would study parabolas and then cubics and polynomials in general, and then you would study all other types of relationships. Before I move on, does anybody have a question about this? Comments, concerns? All right, so sweet. If I go to the next page, then you studied polynomials in general. Now, again, if you don't remember what a polynomial is, that's not the end of the world. That's fine. You would have studied things like quadratics. Maybe something that comes down like this. So these guys, this guy right here would be a parabola. What did this equation look like? It was ax squared plus bx plus c. Some of you are probably having nightmares hearing that. It ain't gonna kill you though. And just in general, we could have, something like this. So this guy over here would be a third degree polynomial. So we might write something like, here's some scary stuff you may have seen before. A sub 3 x cubed plus a sub 2 x squared plus a sub 1 x plus a sub 0. So these are things that maybe you might recall. You definitely would have studied in an algebra class. How much you remember is, well, actually, it's immaterial right now. We're just trying to remind you that if you have relationships between two variables, it is possible to visualize many of them on a graph. So once you got through polynomials, you studied other creatures. Does anybody have a question? So let's make note of that. So you also studied rational equations and likely logs or logarithms and exponentials. So so perhaps you remember some of these. So let's just draw 3 examples real quick. So I'll draw 3 xy axes. Well, I guess I could have drawn these. So what is an example of a rational equation? Well, this is something like the inverse function, which the graph looks like this. How do I get this graph? This is y equals 1 over x. Then you have something like the natural logarithm. We'll use a different color. Perhaps you know what this guy looks like. Its graph looks like this. And then we also had these things called exponential functions. And one of the most important ones was one where you wrote y equals e to the x. Now, many of you have probably seen exponential curves before, whether it was in a class in chemistry or biology or math. They turn out to be quite useful when trying to explain many things, and that's why we study them. So again, this is sort of just a brief review of things that you likely covered at one point, and you might even forget, and that's fine. No one's asking you. We're not testing you on any of this. By the way, I don't even know if I'm going to test you on anything for the remainder of the semester. Does anybody have a question about these?
All I can say is it hurts my brain.
See, that's the problem there, Liam. He doesn't need to.
But it does.
Beautiful. Look at these beautiful pictures. Yeah. Now, there's no doubt this stuff. Look, there is no doubt that many of us have bad experiences with math, particularly equations. Luckily, and I don't want to say luckily, but you know, it's not really necessarily all your fault. I mean, there's no doubt that math education could use a lot of work, particularly at the lower levels, and it turns many of you off for whatever reason. But then again, many of your family and friends don't help because all they do is tell you that you're left-brained or right-brained, or that some people get it and some people don't, and then they mock it. That's never good.
This is why I envision the problems doing to me.
Yeah. Oh my God. Are you typing something?
Just trying to play a sound, but it's not working as usual.
See, that's, what do they call that when you want something to happen? And see, there you go. You're going to drive yourself nuts.
Yeah, pretty much. I'm just happy my computer's actually running at a normal temperature right now.
Yeah, mine is too, which is weird. All right. So let me remind you of a couple important things about this. Well, let's do one more example before we go on. We'll make this one nice and pretty. It'll kill time too. So let's draw this axis. And then we're going to get a circle. That's what we'll do. We get a red circle. Red is beautiful. So let's see if I can get this to work. Okay, so you also learned about circles. So you might, and circles usually scared people, but we got to remind you. So what was the equation of a circle? If this guy has a radius r, centered at the origin, the equation would be something like x squared plus y squared equals r squared. So if that wasn't scary enough, now some more sort of scariness. So associated with circles is the famous number pi. What is pi? Pi is what's called a transcendental irrational number. That means nothing to you, but what you can think about is it means that pi is a decimal expansion that never ends. So this is an infinite sequence of digits. Pi never ends. So, you know, the first few digits that any of us ever memorize are usually 3.14, but I like to remember 3.14159. That's where I go. Some nerds like to memorize 10. I guess a few years ago, some Chinese dude memorized like 10,000 digits of pi.
That's a waste of a life.
Liam, you want to lose your mind if you want to see what weirdos do. If you're bored, Google this. Google number file pi and watch that video of these nerds.
Number file pi.
Yeah, go check it out.
My question is, when do they stop like remembering the numbers and just start making shit up?
What do you mean by that? What do you mean making things up?
Well, how do they like, oh yeah, it's infinite, and like they just like keep on rattling off numbers?
That's a good thing. That's a good question. It's not, they're not making anything up. I mean, so here's the thing, if you want to see the complete details of that, you got to go to the internet and just Google Wikipedia talks about it. There's a whole Wikipedia page for, as the evolution of humans, how we've learned more and more numbers of pi. Essentially, it comes down to computers now. How do you know? So that's a great question. If I say to you, how does a calculator work? Most of us don't know. If I said, when you type pi into a calculator, how does it know that it's 3.14? These kinds of things. So the crappy answer, or as you would say, the shitty answer that I would tell you is you don't know enough math yet to make sense of it. And that's not disrespectful, but you need to learn about calculus to truly understand, and for that matter, define pi. So one of the projects that we do sometimes with our math majors is they might do like a graduation project where they analyze pi from a rigorous standpoint. So I believe your question is, how do we know what these people are telling us about pi? Are they just making it up? And the answer is no. And the reason is, if you understand how calculation works, and I don't mean calculation in the sense of like what you learn in high school or elementary school. I mean in the sense of rigorous calculation, then you could go to a computer and you could, if you wanted, write a computer program to determine pi to any, let me actually look it up. Right now, I can tell you this matter-of-factly. So
there's like no part of pi that ever repeats, pretty much.
So believe it or not, and this is sort of an offshoot of your question. Okay, so right now, according to, in March of last year, humans now know 31 trillion digits of pi. So now, of course, you might say that who needs to know that? Well, Liam, you just pointed out an important fact about pi. So when you were a kid in school, you would learn how to do long division to write fractions as decimals. Like you guys know, like if you take 1/3, what's another way to write 1/3? Well, it's 0.33333333, and it goes on forever and ever and ever. But the difference between that infinite thing and pi is that 1/3 has a pattern. It is 0.3333. It repeats threes forever and ever and ever. Other numbers, when you take their decimal, like 3/4, they terminate. If you take 3 divided by 4, you get 0.75. So what fractions do is they either terminate or they have a pattern. But there are some numbers out there called irrational numbers. The square root of 2 is one of them. Pi is one of them. Their pattern, or excuse me, there is no pattern. There is no pattern in pi. So in that thing I told you, if you're bored to Google, what these nerds do is they write out like 1,000,000 digits of pi, and they do it on a runway at an airport. People have been studying pi for centuries, and the reason is there's all kinds of fascinating properties. And the fact that there is no pattern has actually many implications in things like that you wouldn't think they are, like cryptography. So encryption on the internet, for example. How do we make passwords safe? Believe it or not, pi is associated with that. Not directly, but indirectly. And pi is about to be very important to what we do. So in many ways, pi affects your life and you don't quite realize it. But you make a good point if we go back to the original point. How do we know people aren't just making this up? Well, look, it's hard. It's hard for me to convince you without showing you the actual math that I'm not just lying to you. But I'm not lying to you. There is a number pi. It is associated historically with circles, but it has many, many more practical implications than that. So there's so much you can learn about this on the internet. What do we do with kids? When you're a kid, we probably take, does anybody remember what a compass is? It's like a tool you might remember as a kid to draw perfect circles. You might have taken a bunch of circles and then put a string around their edges and then tried to take this circumference and the diameter, and you get this 3.14. But to actually define, if I can share something with you. So I'm gonna share an internet page with you in a second.
The only thing I hate about compasses is that you have to always have that special pencil that comes with it.
All right, and then it doesn't fit. You have to get a new one. So
Right.
what I'm looking at right now, hopefully you see it, is the Wikipedia page for how humans have, how much about pi we've known throughout the years. And so if we believe written history, then this is sort of what we've known, that for many, many years, all we knew that it was approximately 3. But as the years progress, you know, as I scroll down here, you'll realize that like in the 1700s, we knew that there was like 100 some digits in pi. Well, we knew since pretty much the ancient times that pi would be infinite. Believe it or not, they've known these things. They knew about irrational numbers a long, long time ago. They just didn't know how to compute them because they needed computers. Because guess what happens when you want to do something that takes a long time? In the words of Liam, you die before you get done. So that's why you'll notice that humans only knew a couple hundred digits of pi up until roughly, you know, the 1900s. And then in the 1940s, we were able to compute more and more digits of pi because of the advent of the personal computer. Or not the, excuse me, the personal computer, I lied. Once the computer was introduced in the mid 1900s, now what you're seeing is we're now learning more and more digits of pi. And almost all these computer programs that they're using to compute pi are not elementary. You would not understand them unless you were had a very, very sophisticated background in advanced mathematics. Many of them I wouldn't even understand because I don't study that stuff. Point of this is you learn, look, in the 1960s, and by the way, look at this thing on the right-hand side of this Wikipedia page. You'll notice that there's a time, it's telling you how long the computer ran before it determined these digits. So like Liam, you and I were joking about our computers warming up. Can you imagine how hot your computer is if it was crunching numbers for 70 straight hours?
It'd probably like shut down.
It would. You wouldn't be able to do it on your laptop or your, or as you say, your tower.
Well, I mean, I do have a tower.
Yeah. So what these computers are different. They're not like user computers like you're sitting on. These are many hard drives, or excuse me, many CPUs put together, supercomputers as they are. And you look in 2009, they ran for 600 hours. Excuse me, 2002, someone had an algorithm that ran for 600 hours. Do the math on that. That's a lot of days. Look at these ones, 130 days, 90 days. So what this means is somebody's actually hitting enter on their keyboard. And then 90 days later, the answer has popped up. Or 371 days later. So these are some sophisticated nerds. You got to really like numbers if you sit around for 300 days.
I'll not do anything.
Yeah. There was actually a movie about this. Some of you might like it. It's called Pi. It came out probably about 20 years ago.
Isn't that a horror movie, though?
I don't know if it's a horror movie. It's one of those artsy films where you kind of have to, it's basically just a dude sitting in his computer the whole time. It won lots of awards years ago. I mean, I'm not saying it's great, but if you're interested in it, there's a movie. Some of you might. So, I don't know. Look, there's lots of cool videos you can watch about this if you're interested. You don't even have to like math. It's quite fascinating that people spend so much time trying to get to the bottom of this stuff. Okay. Does anybody have a question? So let's go back to the whiteboard. And let's make sense of that. So pi, or before we do that, so another famous number, and I'm using famous because they show up in nature, believe it or not. So E is a famous number. What is E? E is 2.718, and this also goes on forever and ever and ever. So why do we say this number's famous? Well, we say it's famous because it happens to be very good at explaining things that arise in nature. This number E is used, it was originally found, if you Google it, it's not hard to learn about E as well. It was originally discovered when they were studying compound interest, which is how banking works, which is how credit works. So this number goes on forever and ever and ever. So I don't want to spend much more time on this, but if we can compare it to a more an example that you might have a little more familiarity with. So pi and E are irrational. So you might remember that term from a math class. So if you're interested in learning about it, you can Google it. The square root of 2, which is 1.4. I mean, again, you could spend your days reading about the square root of 2 and how many issues it caused throughout the history of the world. So this guy is 1, 4, 2, 1, and this guy also goes on forever and ever and ever. No patterns. So let's so compare that to other numbers. You know, I mentioned this about 5 minutes ago. So compare that to what we call rational numbers. Those are guys that either have a pattern or end. Does anybody have a question before I turn the page? You're not going to see all this if you read the book, because the book just assumes you're familiar with these numbers. And I, for one, I don't like to do that because there's enough scary symbols. I sort of would prefer that we give you a little review background on this. I think it's a little easier. So you can compare with the rational numbers, such as 1/3, which is 0.333, and that goes on forever. 3/4, which is just 0.75. So let me make that point again. This thing has a pattern. This guy ends. Those are called rational numbers. So what usually happens in like an algebra class, like the very first day, is the instructor will review irrationals, integers, all these names for numbers. And what normally happens for most human beings, myself included, is we zone it out. And that's likely what most of you did, because I did the same thing. But there was a few times in your math education where you learned about these things. And right now it's nice to sort of distinguish. So what humans are doing, and this is another thing that sort of seems like we're cheating, what humans are doing is the number 2.718, blah, 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 blah. That number can't be written down because, well, it's infinitely long. It never ends. So what we do is we invent a symbol for it. So why do we call it E? We call it E because the person who discovered its last name started with an E. His name was Euler, E-U-L-E-R. He discovered it, so his name, E, goes for him. Why is pi the symbol we chose for 3.14, blah, 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 blah? That goes to whoever started. Someone created that a few hundred years ago, and it stuck. I don't remember the history of that. Square root of 2, that again, this is an abstract symbol for a number that we can't write down because its decimals never end. So what we typically do is we approximate them, which is completely fine. So I'll end this conversation right here. To learn, so to understand more about how pi e square root of 2 are defined, you need calculus. So okay, so that was sort of our review. Does anybody have a comment before?
Thank you. Have a good day.
You're leaving?
Oh, no, I'm not. You said you were about to end this.
Oh, no, I didn't say that. I said I'm going to end that.
Oh, okay, cool.
We're going to get to some things that's, well, for some of you, this you may have seen before. But now what we can do, I like that. That's good ass kissing fakeness. Cool. You don't want class to end, even though you guys can't wait. Don't forget there's no class Thursday. I say class, but it's Easter or not. Well, this weekend is Easter. So since we are a school following the Catholic calendar, we will not have class Thursday. It's also a good point for me to remind you that there's no due dates in this class. I don't care if you turn everything in the very last day of the semester. That's fine. Well, we'll talk more about your grades later, but just don't stress about them right now. That would be my advice. If you have the time and the means to learn more stuff, please try. But don't worry about failing this course. You're not going to fail. Well, unless you want an F, I'll give you an F.
So just give us all Fs then.
You know, when I was in school growing up, you laugh about that, but like it was something strange about the United States. I don't know what it is because I never met other people to tell similar stories about other parts of the world. Like of all the people I met who came from other parts of the world, they never told me stories like this. But when I was growing up, kids like brag. They were happy to do shitty in school. Like I had friends who would be happy to brag that they did bad on tests. It's like such a weird thing. It's like an American thing. Like I suck at math. Look at me. Ha ha ha. I never got that. That's very strange, but that's what we are. So maybe some of you want Fs. Some of you like, you can laugh later and, you know, when you get your paycheck, maybe you go, 10 years from now, you're like, I'm going to go buy a BMW. Then you buy one and then you say to yourself, see, I told that stupid ass O'Grady I didn't need math. I cheated in his class, or I didn't even learn anything. Here I am driving a BMW. And then you're laughing. Ha, 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 ha. That'll be some of you. All right. I'll be laughing too, though. Hopefully I'm still alive in 10 years. Okay, so.
Hopefully you're alive tomorrow.
That's a good point, Liam. But I don't like to think that way, dude. We got to get you to have positive aspects, Liam. Think of the happiness. Okay.
Yeah.
So here we go. So an important So here we are. We're ready. To write down. We're going to start with the simplest one. So we're ready to write down what's called the standard normal distribution. That's a lot of words. Okay, so what is the standard normal distribution? Well, it looks like this. It's the equation y equals. Now I'm going to write out front 1 over the square root of 2 times pi. And you're going to say, why in the hell is that there? I'll explain in a second. And then it's e to the 1/2 x squared. Yikes. So let's let those scary symbols marinate for a second. Don't let them kill you. Please, please, please do not let them drive you nuts.
See what happens. But regardless of what happens, we're totally prepared.
Does anybody have, excuse me, a question about this? Now, scary. So let's say a couple things about this that are very useful. Excuse me. So, oh my God.
Corona.
Let's hope not. All right, so given, well, let's say it the following way. Using a calculator, you can graph this. In calculus class, you learn why the graph looks the way it does. So let's modify this because I'm running out of space. So let's say you learn why the graph looks that way. So if I just draw an XY axis, here's what it looks like. So this is a it's a curve that looks like this. So I didn't draw it perfect. Let me try that one more time. Good, that's better. So we often refer to this as the bell curve. So there's some important points that this thing hits. Let's label them. And it might take a moment for you to get to the bottom of this. This point right here, I want to use black. So this highest point right here, the top of the bell, what is this? Well, when you plug 0 into the expression, the only thing that remains is this. That's scary. Ooh, excuse me. And then you can really think of this as being right about the number 1, and then this is right about the number 2. This is right about 3. And it should be symmetric with the y-axis. So whatever you see on the right-hand side is perfectly the same on the left-hand side of the y-axis. Does anybody have a question about this? So if you Google the bell curve, are you not a list? We talked about this. Can you listen to R. Kelly anymore? I don't think so. Okay, so Anybody have a question? Okay,
Numbers hurt my brain.
yeah, all right. Well, okay, so here's some more good and bad information I'm going to give you, depending on your feelings on it. So, in applications, it is important to know certain what we call areas under this curve. So, for example, I might want to know this shaded region that I'm sort of highlighting. I might want to know, what is this area? So the precise solution to this problem is done in calculus. Well, we don't need to know the precise solution to this. So what we need to know is something slightly different. So the precise So the precise way, if you want to learn about this, you need to take calculus up through calculus 2, if not higher math courses in probability and statistics. But we don't care about the precise way right now. You have to trust us that what we're going to teach you is correct. So we will use calculators and/or tables to compute these areas in this class. And that's how most professionals would do it. So what do I mean by that? Well, let's think about this. Every one of you is, well, maybe, I don't want to say every one of you, but I'm assuming every one of you knows what an airplane is. Every one of you knows what a car is. Most of you have probably driven a car. Most of you have flown in an airplane. Well, maybe not most of you. Some of you have. Just because I've driven a car, does that mean I know a damn thing about how to build an engine? Do I know how a car necessarily works? Maybe I do, maybe I don't, but I don't need to know how an engine works to drive a car. Just like I'm sure most airplane pilots do not know how to build a jet engine, nor do they understand the mechanics of how it works. However, they can operate it. That's sort of the analogy or the metaphor I'm going with here. There's enough people that can compute these areas precisely, and what they've done is they've written them down in tables, and we've programmed calculators to do it for us. And so for us, we don't need to know the precise way of calculating these areas. All we need to know is how to get the answer. Now, what I'm telling you is if you want to learn the precise way of calculating areas, you need to use calculus. Does anybody have a question about this? Now, what's fascinating is questions like, why does this square root of pi show up? And believe it or not, that's not made up. That's not just gibberish that math people make up. It actually has a connection with the important questions we're trying to answer. So what we do is we associate these quote unquote areas with probabilities. Okay, so excuse me. Does anybody have a question? Okay, so before we show you how to do that, let's do some notation. So it is convention to use Z instead of X when using the standard normal distribution. So we have conventions. This is one of them. In the United States, we drive on the right. In England, they drive on the left. That's convention. Here, we use this convention. Instead of writing X, we use Z. So we might write this like this. And so that means that the graph, the horizontal axis, we usually refer to as the Z-axis. And then the vertical axis is the Y-axis. So let me be very clear with that. We would call this the Y-axis, and we call this the Z-axis. And so the curve's going to look like this if I sketch it. Does anybody have a question about this? You might remember some weird math terms like asymptotes. This thing has asymptotes, these things called horizontal asymptotes, and that means that that blue curve never, ever, ever touches the Z-axis. Does anybody have a question? Okay, so how do we make this association with probabilities? So here we go. So what you want to think about is, how do we connect areas with probabilities? So that's sort of the question, and we're going to do it the following way. Notice I keep writing area in quotation, and the reason for that is I could offer every one of you $10,000 right now. I could PayPal you in a second if you could define area for me. And unless you've studied calculus, you can't. You don't know a technically sound definition of area, and that's not an insulting statement. That's just a fact. And think about it. Ask yourself, could you write down a logically sound definition of area? And it would be impossible for you unless you knew the nuances of calculus. And so that's why I'm writing area in quotations, because I want you to think of area in a naive sense, that it's just the obvious thing we're talking about. What is underneath or between curved space, like the area of a circle or a rectangle. Okay. Here's how we do it. The probability that Z is between some number A and B, this is equal to the area under the curve from A to B. So if we draw a picture, to help illustrate this, hopefully it will make some sort of sense. So I want to draw my curve. My curve's going to look like this. It's kind of sloppy. Maybe I'll try that one more time. I'm trying to make it so that these curves look as symmetric as possible. So there's one. It's a little better. So let's label one of these points A. I can draw it anywhere. I'll put it here. Let's say this is A, and then let's say this is B. Then the area of this shaded region, let's be more careful here. So the green area equals the probability that Z lives between B and A. Now, you might not understand how to interpret this yet, and it also equals the probability that A is less than or equal to Z is less than or equal to B. So we're not distinguishing less than or equal to's right now. So that's another subtlety we'll talk about. So let's make sure we put this area in quotations. I think that's important. Does anybody have a question? Okay, so we're going to give you some problems on determining probabilities, and the question is, how do you do it? Well, like I said, there's two naive ways of doing it. The first is to look them up in the back of your book. There's a table that tells you this. And the second, which is easier as long as you take the time to learn it, is to use a calculator, whether it's on your phone, whether it's on the internet. You don't need to buy one. There's plenty of free calculators. Maybe I'll put some links up on Canvas if you're so interested. There's also there's also lots of good YouTube videos to show you how to do this. So before we end, it might be worthwhile showing you why we haven't really said, like, you might be thinking, why are you calling this a distribution? Why are you talking about probability? We haven't even talked about an experiment. Or in the words of Liam, are we done with coins and dice? And so you might not really be thinking, where in the world is probability entering the picture? We'll get to that. But why are we calling this a probability distribution? Well, let's go to the internet. Hopefully you could see this. I'm going to go to a calculator and I'm going to type something you might not understand. I'm going to integrate something. And integrate is the mathematical thing we use to get, that's how we get area. So what I'm going to do is I'm asking the computer to determine the area under this curve.
We still just see the slide.
Okay, that's not good. We'll show you in a second. Why didn't it share it? So what I'm typing in now is I'm typing in some fancy math terms to get it to compute area. So you might not make sense what I'm typing in, and I don't even have to spell correctly. It knows what I'm doing. What I want to point out to you is the following. What I'm circling, and maybe I'll zoom in on it. Not going to zoom? Of course you're not. You'll notice that this number, that when you find the area under the curve, the total area is 1. And that tells us that, just like we studied weeks ago, the total probability has to be 1. If that's the case, then we can use it as a distribution. So why we're interested in this function, this equation as it were, is because its area is 1. And what gives it the area 1, so it's important to point this out. Let me go back to the whiteboard. What's important to note is, let's go back to this thing. The total area here, which is kind of a mind F. If I take this area under the curve, the total area equals 1. Does anybody have a question? So we'll give you some problems to do, and and then we'll show where this becomes useful for actual applications the next time we meet. But right now we have to sort of get our feet wet and get you to compute some probabilities. And then once you're able to compute them, we'll show you how to compute actual probabilities, not just made up ones. Does anybody have a question or comment before we call it a day? Now we're done, Kevin.
Oh, okay.
Does anybody have any questions? All right, if you guys don't have questions, I'm going to stop.